Good evening, and I welcome you all to this week's Saturday talk on solar fuels. Can we store sunshine for a rainy day by Mr. Oshnik Maurya? It is our honor to invite Mr. Maurya, who is a PhD candidate at physics at the Institute of Chemical Technology, Mumbai, and a material scientist working at the forefront of nanomaterials, photoelectrocatalysis, and green hydrogen technologies. With over 6 years of hands-on R&D experience, he has contributed across the full innovation cycle, from material synthesis to device fabrication to electrochemical characterization and performance optimization. He has published widely in high-impact international journals and actively engages in clean energy innovation, intellectual property strategy, and science policy interfaces aimed at advancing climate-aligned technologies. A young and dynamic thinker, I thank Mr. Maurya for joining us today for the 205th Saturday Talk. Over to you, sir.
Thank you so much for the introduction. So, as we I wanted to start with this. So, the topic what we selected was about the solar fuels and can we store sunshine for a rainy day. So, this is kind of metaphor. Actually, rainy day does not mean anything. This is for those technologies because, when we talk about solar cell technologies, ideally when you have sun, that time only you can use that. Otherwise, you need some batteries or grids, to store that energy into the form so that it can be used for the next time. So currently I'm doing my PhD under Dr. Archana Kalekar and Professor R.R. Deshmukh. Both are located at ICT Mumbai. Now let me start with this. So this was an interesting article I found last year. One of the parents they decided to have their baby to be the carbon neutral. So what exactly carbon neutral meant for them was on an average, for example, whatever is the CO2 emission values for a particular individual, they planted those many trees in order to compensate the CO2 production which will be there from their child. And so this was kind of world's first carbon neutral baby. When we come into 2025, I belong to the generation where I am born in 1995, so kind of millennia. And now we have generation beta, which is they started from 2025. And because they are born into a tech-driven world, but alongside the tech-driven world, we also need to understand that we need to, work towards the ways which can reduce the impact of climate change. Because that generation, when we pass on all the resources to their generation, they should not feel that we have done injustice to them, and therefore sustainability should be the key agenda for doing any of our research work. Now when we talk about climate or climate correction, so these are not just buzzwords. People still they deny that whether there is really global warming or not, or whether these are only just the fake propagandas that is being spread throughout. But these coming from the scientific background, we know that there is climate issue happening, and these are not just buzzwords, but we need to take a call to action. And we need to take bold, decisive steps to ensure that we leave a thriving, sustainable planet for generations to come. Before we go through this, now let me come back to one of the crises. When in 1973, there was an Arab oil crisis where the Arab those Arab nations. So there was an Arab oil crisis, and at that time, most of the European and Western nations, they thought that we should work on those technologies where we don't have to much depend on oil. So kind of oil-free future where we don't have to just depend on oil, and we have to look towards the other alternative technologies. Then this is one of the classic papers in our field that is called as Honda Fukushima effect, where what they did was they took the TiO2 semiconductor and they just shined the light on that, and they could split water into hydrogen and oxygen. That was in 1972. Post that, then in 1992, then United Nations they started to develop their programs, and then they came out with Sustainable 21-point plan for development goals. And then the plan listed various things that are good for humanity. Then we come to 2015, where we had Paris Agreement, and as we know that the global warming is going to affect everyone, each one of us, regardless of race, religion or gender. So the Paris Agreement, they wanted that the temperature should be limited to just 1.5 degrees Celsius. And it was envisioned in 2015. And post 2020, we still have several challenges in terms of to move away from the fossil fuels and to work towards the global warming problems. Now, if you think, when you take the title of my talk, so the first thing what you understand is the solar energy paradox. Solar energy is abundant in nature, as we know, because but it is time dependent, and it is also geographically dependent. It depends. Like for example, India being a tropical country, the solar shines throughout the year. But like when you go towards the polar regions or the other countries, some countries they have very limited use of solar energy. So it is time independent. And however, when we talk about the energy demand, what we as a humanity have, it is always continuous. It's like, I mean, it is, so solar energy, it is kind of discontinuous, and the energy demand is continuous. So this is what I call a solar energy paradox. And if you talk about the energy storage time scale, so currently we have like batteries. So these batteries can store energies for seconds or hours, but they cannot go on for days, right? And then you have the pumped storage systems where you can store the energy 2 days. While when we talk about the fuels can be any fuels. They can be used year round, and they can be used throughout the months or seasons. And therefore, it also becomes challenging, to have the good storage things. So limit of an all electric system. If we have everything all electric and we don't have anything related to storage, so what will happen is like heavy industries, they need huge amount of electricity and huge amount of energy, and it cannot be completely fulfilled by the electric alone. So they need alternative fuels. Also shipping, aviation, these companies where they have a huge they are energy intensive industries, they rely so much on energy, and therefore those energies cannot be completely electrified, and therefore we need to look towards the fuels. Now ideally, if you talk in layman's language, what is a fuel? So fuel is any energy which is stored in chemical bonds, and whenever required, then we can utilize, we can break those bonds, and then we can utilize that energy to do our work. So before coming to this fuels, now traditionally what we have been following was the fossil fuels. So fossil fuels, this can be, kind of ancient stored sunlight, and solar fuels is the talk, of the research community, where you utilize the solar in order to capture that, and you can convert that solar into, some other clean forms or some other chemical forms. Now, this is one of the things what I wanted to highlight was like the amount of solar energy that strikes the Earth's surface in 1 hour is enough to support the world's energy consumption for an entire year. This was something way back taken in 2020. So the figures might have changed, but one thing we need to know, solar is the only key if you want to decarbonize the entire sector, and we need to look for all the processes, all the technologies that utilize solar in their mainstream. Now, what are the solar fuels? So like solar fuels, they can be utilized to make consumer products. They can be used for energy storage. There are certain technologies that have started to working upon doing the wastewater treatment, and then to do emission reduction, and to also work towards the specialty chemicals. Now, if you can see the definition of solar fuel, so these are the chemicals that are produced using solar energy, and when on demand it can be released. So what are the typical examples of solar fuels? One of the most widely researched and one of the most funded solar fuels is hydrogen. Second comes in the line is ammonia. So we have also started to hear the terms called as green ammonia synthesis. So those things are ammonia. And then you have synthetic hydrocarbon, where synthetic hydrocarbon is the hydrocarbon where we utilize CO2. So we take CO2 from the atmosphere, and then we can convert CO2 or CO, that is carbon dioxide products, we can convert into methanol, ethanol, or other hydrocarbon product. And also we have then solar derived chemicals. So these are specialty chemicals which when you shine light on them and you do some processing, you can convert one form of chemical to other form which is having a higher value. Now among all this, why hydrogen leads? Because hydrogen is the simplest molecule. It's having just one proton and one neutron. It's a carbon free molecule. It is already being used in industry, but typically the hydrogen which is used in industry is not green, and it has a very simple chemistry. So we will, next few slides I'll focus on hydrogen, and then we can go to the other technologies. So when I was talking in slide 2 about the sustainable development goals, the United Nations has given a list of several goals, and being a researcher myself, we also always strive to do our research so that one of the goals can be of these United Nations development goals can be solved. Even any startup or any company, they should always look into this roadmap and try to align their objectives and policies towards them. Now, Government of India in 2022, they launched the National Green Hydrogen Mission. So by 2030, what they planned is they need to have 5 million metric tons of green hydrogen by 2030. This can be done by having a gigawatt scale of electrolyzer plant establishment. Then because this green hydrogen mission, the targets are very heavy, so you need to have like new expertise, new kind of jobs, and they expect that like 6 lakh new jobs in this domain will be created, and doing so the 50 million metric tons of carbon abatement in different industrial sectors can be done. So then this is all about the green hydrogen buzz what is there in the current news. So the Europe is doing their part of going towards green, that is using the hydrogen as a clean and circular economy. Then we have like different countries, Saudi Arabia and all the major countries, now they have their own national hydrogen green hydrogen policy roadmaps, and many countries have started to work upon it. So now this is the slide I have shared from US Department of Energy. So what they want is they want to have a systematic coordination across Department of Energy, different departments, and this can be in terms of research, development, demonstration and deployment, and across the entire H2 value chain. Now from the if you go through the international the green hydrogen policy roadmap, this is point number 2.6, where the government has identified different kind of projects. Some projects can be done in an immediate timeline, some will require 5-10 years, and some are long-term vision. So in the priorities, R&D priorities, if you could see, the one of the projects that the government is considering is photoelectrochemical water splitting. And photoelectrochemical water splitting is one of the solar technologies that can utilize solar to convert H2O into hydrogen and oxygen. Also they have given certain targets, for example like 5.7 per kg should be the cost which is currently now, and what they expect for any technology in order to commercialize. This is the thing I have taken from US Department of Energy. So if you can see the topic 1 in their NO4, the projects that they want to fund up and they want to scale up is to develop and demonstrate PEC water splitting technologies. So PEC is photoelectrochemical water splitting, and because currently the technology is very expensive, because the choice of catalyst is very high, the platinum and those expensive elements are used, and the government and the funding agencies want to go away from those high expensive elements towards lower cost and scalable synthesis and fabrication techniques. Now this is the hydrogen shot program. What US they have launched is 111, that is if you can reduce the cost of 1 kilogram of hydrogen, green hydrogen, in next 1 decade, that by 2030, and if the price is $1, then only we can think of replacing hydrogen with other fossil fuel technologies. So this is hydrogen shot $111 program. Now, as I was discussing, like when we talk about hydrogen, currently in industry, the hydrogen is produced by different methods, and the method of production of hydrogen and after the procedure, what is the kind of hydrogen that is used. So that will decide of the different colors of hydrogen. Broadly, when we talk about any class of hydrogen, so we have 3 types of hydrogen, that is gray, green and blue. So when I'll just get into very minute details. So when you talk about gray hydrogen, if you can see, in gray hydrogen, the input is fossil fuel. What you will use is you can use coal and petroleum. So you use that, then you do the water splitting reaction, and then you generate the hydrogen. Because here the input is fossil fuel, that is carbon intensive, and the output is hydrogen, so it is called as gray hydrogen. Now better version of gray is blue. So what you can do is, again you use the fossil fuel, but here in blue hydrogen, what you do is, whatever the CO2 is released in gray hydrogen, that CO2 you can capture, and using many countries have developed CCUS technologies, that is called as carbon capture and utilization and storage technologies. So you whatever the CO2 is released after the processing of H2O, that you can capture, and then when you release the hydrogen, it is more better. So this is called as blue hydrogen. And when you go towards the next, the most environment friendly hydrogen, that is green hydrogen. So in this, rather than using fossil fuels, what you use is you can use renewable energies. That renewable energy can split water into hydrogen and oxygen, and because the output is hydrogen, you don't have to worry anything about CO2. So this is the most efficient way and most cleanest way to get the hydrogen on the for the commercial use. Also, there are various other methods like turquoise, red, purple, green, yellow, white, and there are there is an entire spectrum of hydrogen that has been envisioned, and people have started working upon these different shades of hydrogen. Now when I talk about the solar fuels, if you can see in the graph, you can see like the first diagram shows the current linear economy. What happens is currently what we follow as of now. So we what we do is we take the fossil fuels, we do some treatment, and then either the fossil fuels can be converted into chemicals. For example, fossil fuels can be converted into glycerol, it can be converted into some other forms, or then the fossil fuels can be burnt and then they can be converted into energy. Once these things are done, the entire things, if there is some sort of reuse or recycling, it will be done, and all the remaining waste is then disposed of. So either it goes, either you incinerate it, which can release a huge amount of CO2 and other atmospheric gases which are very harmful to the environment, or you can just dispose everything in the landfill. Now if you talk about the circular economy, which is more towards the solar base, now if you can see here, what we can do here is, or what we can propose here is, you can utilize the solar, that is the sun, and then utilize CO2 that is from the atmosphere. You can combine CO2 with solar, and then you can convert these into the other forms, and then you can also recycle CO2. There are also options. For example, there are also certain industries which produce high biomass, so you can do the biomass pre-treatment, and then these biomass can be converted into there's a term called as upcycling or upgradation of those biomass into some useful products, and this process is more kind of circular loop. Now even same can be done for hydrogen circular economy. So you have fuel cells that can split hydrogen and oxygen, then you have solar hydrogen power plants which can utilize solar, and then they can give you hydrogen and oxygen. This hydrogen can be then fed to fuel cells, and also CO2 from other industries can be utilized with CO2 and hydrogen to chemical plants for hydrocarbons, and this can be one hydrogen circular economy that can be seen in the future. So when we talk about solar hydrogen or solar powered economy, so everything can be done. You can have sustainable fuels and chemicals, you can have waste feedstocks, you can use biomass, and you can convert, and you can also when I do research, many groups are now also working upon plastic upcycling, where the plastics can also be converted into lower toxic forms using solar. Now when we talk about solar, any solar technology, it will always have two components. One is entirely photon driven, that is they utilize photons and then they do the reactions, and then the other is called as thermal driven. So when we have like high concentrated solar light, we can also do thermal driven processes. So solar, this can be classified into thermal driven processes and photon driven processes, and based on thermal driven processes, if you can see towards your on the screen towards the left, you have different technologies that use highly concentrated sunlight for doing their reactions and studying their chemistries. And when you go towards the highly photon driven, so these the technologies that are on the right, these are mostly room temperature synthesis. If you can see, it is 300 Kelvin, which is approximately what we have towards the room temperature synthesis. So we have photothermal catalysis, then we have photovoltaics plus electrolyzer or PEC photocatalysis, or you can reform your fossil fuels and biomass into some useful products. So I will more focus towards the photon driven part now. Now when we talk about the solar spectrum, if you can see, if you the entire spectrum what we get on the reaching on Earth's surface, if you take that as 100%, approximately 4% of that spectrum is UV light, and 44% is visible light, and more than 52% is a higher energy infrared light. So our approach is, because we need to look on the technologies which can harness the maximum spectrum of light. That is always our key work. So as I told you earlier, like there are few technologies which can be done at ambient temperature and pressure, that is in room temperature, which can be more commercially it is viable. So the first technologies that I want to focus is called as photocatalytic reforming. Now I want to break down this word. Photo is light, catalysis is to use any material or catalyst to reduce the rate of reaction, right? So photocatalysis. Photoelectrochemical is where we utilize both the light, electro is the electricity, and the chemicals are any, you use the catalysis and then you can do the conversion. And the third is called as PV electrochemical reforming. So photovoltaic is what are the commercial solar cell technologies what we have now. So silicon solar cells, they are highly commercialized. They have, they have very cheap price. And what we can do is whatever is the current that is coming out from the photovoltaic technologies, you can utilize that as an energy source to do the electrocatalysis of water, that is splitting of water into hydrogen and oxygen or to other to other chemicals. So currently if you talk in terms of maturity, because photovoltaics, they are very cheap, electrolyzer technology is commercially viable. So most of the thing, whenever you talk about green hydrogen, people will always talk about PVEC technology, that is photovoltaic integrated electrochemical technologies. However, the photocatalytic reforming and PEC, these are more of lab scale, and they are now being tried to towards the from lab scale towards more prototype and industrial scale. They are being now targeted. So if you can see the photocatalytic, what happens is the light will fall on the material will get activated in presence of light. So whenever the activation takes place, electrons and holes will get generated in the material, and these electron and holes will then be utilized to drive the reactions. So the photocatalytic technology, when we talk about, either you can make the sheets of those materials, or you can just make the powder and disperse in the solution. PEC technology, what happens is we have two different electrodes. So we have on one side, it is called as photocathode, and the other part is called as photoanode. And when you shine the light on the light active material, in the presence of light, these materials get activated. Again, the mechanism remains the same. They will generate the electron hole pairs, and these electron hole pairs, then they can do the necessary reactions. So as I told you in the previous slide, so now whenever we talk about sunlight, we have seen like leaves, right? The leaves are the best example they are the most optimized version of utilizing sunlight, converting the molecules into some other useful forms. So when we talk about the photosynthesis process, what happens is the light falls on leaf, the chlorophyll, then they have several reactions. What they do is they convert the CO2 and water into useful products. So that is in forms of glucose, right? The fruit that we eat, it is like so actually it is your sunlight which has converted H2 and CO2 into some useful product. So that is your natural photosynthesis. Now parallel to that, what people are now trying to do, or the scientific community is trying to do, is can we mimic this, or can we mimic the artificial photosynthesis and do that for our natural can we do that for artificial photosynthesis? And that technology is called as artificial leaf. So as I told you, like in the previous slide, what is exactly light falls. So in 12th standard, this is very basic things. So we have heard about the semiconductor materials. So semiconductor materials, they have the valence band and they have conduction band. When you can see here, the line, it denotes that for water splitting, the minimum amount of the electricity required is 1.23 volt versus RHE. So if the band alignment of your semiconductor, that is the upper band and the lower band, it is in tune of water splitting or for CO2 reduction, if the band will align in that context, then easily the water can be split. So whenever we talk about any photoelectrode material or any semiconductor, as discussed in the previous slide, what are the four things that are required for the photoelectrode material to be ideal? So first, as I discussed in the previous slide, it should have a suitable band gap, energy and band positions. Second is because only the band, getting the band position is not important. Also, once the bands are aligned, they should effectively separate the carrier charges, that is electrons and holes. The photon that is incident on the semiconductor, it should drive the electron hole pair. They should get separated. The more they get separated, the better it is useful for our electrode reactions. Third, it should have a strong catalytic activity and stability. And the most important is whatever the materials we use should be low cost and earth abundant. Now, as I told you in previous slides, like solar can also be utilized to do the waste reforming of our processes. So here they have given, there's an example where some of the raw materials which are widely used in industries like cellulose and polyester and glycerol. So what it can be done? For example, if you can see for the cellulose is one of the biomass. This cellulose can be pre-treated. So pre-treatment can be done by any method. So they have given different methods like enzymatic, physical, thermal, chemical, or biological methods. Once these are pre-treated, these biomass other than biomass, we do have plastics also. So plastics also you can see like PET can be there, and you can just break down this plastic into simpler molecules, and after once these are pre-treated and broken down into simpler molecules after pre-treatment, you get the smaller molecules like glucose and different glycerol and phenol. Now what can be done is, now our approach comes here. So what can be done is, these simpler molecules, we can shine the light on them. This light, when shined on them, this can further break down into some other molecules. Now based on the selectivity of the molecule and the catalyst that are using, you can have different list of molecules. Some molecules after the breakdown can be more it can be toxic or it can be not toxic. So selectivity can be done to improve the the final to avoid the toxicity. And also you can use syngas and hydrocarbons, and you can convert it into different alcohols also. So depending on the industry requirement and the value of the product, you can utilize this to do the solar driven waste reforming process. Now as I discussed earlier about the photocatalysis process, so in photocatalysis what happens is, you have just a catalyst, that is your semiconductor. As I told you, whenever the light falls on any semiconductor, there is a valence band, there is a conduction band. The electron will the electron hole pair will get generated. The electron will move towards the conduction band, and the holes will travel towards the valence band. The holes will then do the different reactions. The electron will do the oxidation reactions, and this will do the reduction reactions. And using just a single catalyst, you can prepare your own do the oxidation reactions. So for example, in this also, then as I suggested told earlier, then you can have a floating photocatalyst. You can do that on sheets. You can coat them with magnetic nanoparticles, and then after the treatment, you can just magnetically recover those photocatalysts. So 4 types what we can see is homogeneous. Homogeneous is photocatalyst is very nicely suspended into your system. Second is heterogeneous. There is a mismatch between the dispersion of catalyst and the electrolyte medium which is used. Then you can make a sheet, or you can also have a floating photocatalyst which you can use. The second type what I discussed was PEC. So it is also very simple technology. Now understand PEC very similar to solar cells. So what you do is, you shine the light on your electrode. Then electrode will have different layers what we have in solar cells. So there is a light absorber that will absorb the light. Then you have HTL and ETL. HTL is hole transporting layer. ETL is electron transporting layers. So once the electron holes pairs are generated, you can separate them through the external circuit, and then you can drive the reactions. Now either you can shine towards the cathode side. So if you can see the figure C, that is from the photocathode side. You can do photoanode side, and if you can try to integrate photocathode and photoanode into a single unassisted device, it is called as PEC reforming, or the artificial leaf, similar to the leaf what we discussed earlier. And also what you can do is, you can use the photovoltaics, and then you can use photovoltaics to do the electrochemical water splitting. Now this is some of the lab results what we have done. So we have used TiO2 as a semiconductor, and we have tried to align the TiO2 along one direction, and to have nano arrays of TiO2. So these are nanostructures which are one dimensional. Why one dimensional? Because we wanted to have a directional when the light falls on the material on TiO2 semiconductor, these charges should nicely get separated, and for that separation, if you have a vertical one-dimensional alignment, this is more useful for improving the PEC response, the photocurrent density what we get from the material. And then if you can see in the first and the second diagram, the right side you can see the transient switching. Now you might be thinking like, what exactly is so if you can see 0 and you can see 6, so the lower part is when the light is off. So as we shine the light, it generates a current. As we off the light, the current decreases to 0. So this difference between the on position and the off is what we are getting from the solar, as I was discussing. So when you on and off the light, whatever the difference you get, that is your extra current that will this is the extra current what we get, and this current can be utilized to do the different reactions. Now this research I have highlighted in some different conferences, and now what also I have studied is when we do PEC water splitting, because when we talk about water splitting, it's the water oxidation reaction. When we talk about OER, we have simultaneously hydrogen evolution and the other is OER. When we talk about OER, it is a 4-electron process. Because it is a 4-electron process, it requires a huge amount of energy, and that is why direct PEC devices are not very commercial, because it is very difficult to break the hydrogen and oxygen bond. So what you can do is, rather than going for breaking the hydrogen oxygen bond, what you can do is you can utilize the glycerol, because glycerol in water, glycerol, one of the products it can give is H2, and we don't have to worry now about OER, that is high, because oxygen it does not have that much value as compared to hydrogen. So when you do this reaction in our systems, what we find is the current density increases. So the same reaction, everything is same. Now we are replacing OER with glycerol oxidation reaction. So along with glycerol, you can study different reactions, and then you can quantify and understand like which reaction is more useful for us. Now I want to go towards my ending topic. So are solar fuels ready? Because this topic has been since last 30-35 years, but there was not so much push, because there was no so much awareness among people. Science people know everything, but to coming towards policy, getting towards a policy document, it's very difficult. So are solar fuels ready? As of now, the electrolysis, that is the commercial technology, it is an emerging technology. However, when we talk about the direct solar fuels, that is photocatalysis and PEC, those are into the early stage. Beyond hydrogen, now most of my work is focused on hydrogen, and little bit I told you about the glycerol oxidation. But now the research groups are also trying to convert CO2 into useful products. So you can convert CO2 into ethanol, CO2 into methanol, or CO2 into syngas, or those things. You can also biomass upgrade. So upgrading of biomass, for example, glycerol can be converted into DHA. It can be converted into formic acid, ethanol. So C1, C2, C3 different products can be converted, and there are also certain chemicals which cannot be produced by traditional ways. So scientists and research community are trying to identify those chemicals and those chemical reactions where you can utilize directly sunlight to convert those chemicals into useful products and value-added chemicals. Now, why continue research? Now, everyone thinks like, the efficiencies are very low. It is not widely accepted as compared to the traditional industries. This thing has a very high cost. So, but we should not forget that any transition, it takes time. For example, if you take about solar came in 1970s, 1980s. 1980s, the solar cell came. But initially when solar cell came, it was very expensive, right? So no one was so much into solar. But like if you see the solar curve of last 10 years, what you find is the price of the silicon solar cell has dropped to such a huge, extent that solar cells have now become feasible. So we don't know now, as of now, like which technology can, go ahead and which will win and which will kill. So we always need to look towards the learning curves, and research community always tries to give you different directions. It is up to the industry and the government to take those ideas and to move towards more commercial approach. Now, what final message I want to give is like, we already can store sunlight. That's not an issue with us. But can we do it cleanly, deliberately, and on a low cost basis? That is a challenge what we are facing now. These are some of the technologies and the startups what I found. So different startups have come across world. My personal experience is, as an continent, Europe has heavily invested in their renewable energy infrastructure. So they are doing huge amount of funding in terms of renewable energy research, in terms of deployment of those technologies. Rest of the world is very far behind. US is behind, India is behind. Most of the countries are behind. So we should learn something from Europe. And because like most of the clean tech startups, whatever they come, they are mostly based from Europe. So these are some examples. What I've given is Rift, and then you have Synhelion. They are trying to convert CO2 to ethanol and methanol, and then you have also the solar gasoline. So solar aviation fuels, if you have heard this term, there's a huge interest now coming towards solar aviation fuels also. And this is one of the, some of the things, PEC, one of the most commercial aspect of PEC. In this PEC, what they do is they utilize the concentrated solar panels and then they use that to drive the hydrogen and oxygen reactions. And this is called the artificial tree. So this is based in ETH Zurich in Switzerland. So I want to end my talk with this, like whenever we do any kind of work, it's like always our priority to have energy and environmental justice, because anything what we the gains or the losses, it should not be gains should be for few set of people and losses should be for few set. Everything should have energy and environmental justice, and always we make sure that there is diversity, equity, inclusion and accessibility. This is a slogan from from one of the government websites. Like whenever we always have Jai Jawan Jai Kisan, but if India truly wants to be 2047 Atmanirbhar Bharat and to be an economic powerhouse, so for doing that we have to invest so much into science, innovation and technology, and that is where the CSR came with this logo of adding Jai Jawan Jai Vigyan and Jai Anusandhan, that is more focused towards science and more towards innovation and technology. This is what I wanted to present. So thank you everyone, and I'm open to questions now.
Isn't there a much cheaper technology, the way we we take ocean water and in open pans, salt pans,
right?
We make salt out of ocean water, and people say that yes, salt is separated with water, and that once it is mixed back with pure water, river water, generates electricity. So isn't there a cheaper way like salt pans?
Salt pans, I have not so much heard about this, but parallel research now, what research community is doing is about the seawater electrolysis, where what it is done is you use the seawater, you do the do the water splitting of the seawater, and then you can get hydrogen and oxygen. However, the issue with the seawater splitting is that, like, when we do the reactions at the cathode and anode side, you have because there is the seawater contains other chemicals, so there is chlorine poisoning happening at the electrode, which can reduce the performance of electrode. Alternatively, what people do then is they use desalination plants. So then they desalinate the seawater first, and that ultra pure water, then they utilize that for seawater electrolysis. But then there are because the two processes are involved, this is very costly for doing. So currently it is more into research state, what I know about the seawater electrolysis. About the pans, I am not having very clear idea, so I cannot comment much about
that. Since solar is not, you can't do it 24/7, you can't run. So you want to bring hydrogen fuel. So it's like you first, in simple words, you just the electricity comes and breaks the water, and you get hydrogen, which is stored in fuel cells, which reacts with oxygen. You create electricity.
Yes, sir.
Yeah. So actually, what in today's world is that solar's efficiency is so low. Like whenever you hit with the if you want to get electricity, there are so much heat loss, and you're trying to convert into hydrogen, and you want to break water into hydrogen. Again, some electricity is lost, and again when you want to react with oxygen in a fuel cell, again some heat is lost, so the efficiency of this is drastically reduced. So how do you think we could mitigate this? Because the efficiency will be very low, and the price will be so high. The input is so high, but the output is very less. So in case, what could we do?
This is the question. Entire research community is already working upon. So when you told about the first, in the slides, what you have seen is first technologies. What you use is PVEC, that is you use solar cell. And when you do the conversion towards the electrolysis of water, those are two different systems. Because there are two different systems, the efficiency will drop as we move from one system to other, right? So in this context, the emerging area is photoelectrochemical cells, where in one system only, the sunlight will fall, it will get converted. Whatever the electron holes are utilized, it can be utilized for getting hydrogen and oxygen. But the disadvantage of PEC is that the PEC, they have very low efficiencies. Currently, the state-of-art PEC in the research, it is around 19%. According to some reports, if the PEC has to be commercially viable in a single system, if you are doing everything, for that, at least the solar to hydrogen conversion efficiency should be around 20%. There are several electrode materials people have started to work upon, but the efficiencies are around 12%, 14%. So I guess next 5 to 10 years of intensive research needs to be done in this domain in order to make this PEC competitive. If PEC becomes competitive, I don't think so we need to do the solar and electrocatalysis separately. That will be kind of future. But currently, as of now, as you told, it is very difficult. There are several losses in terms of there are ohmic losses, there are current there are certain losses which are from the solar to photon conversion, then photon to electric. There are different losses, and individually we need to then focus on first we need to understand as a research community where are the losses happening. And now if you see like many advanced the laboratories in Europe and especially in Germany, they have now started to work upon in situ characterization techniques where during the reaction what is happening. Currently when we do research, we do is like after the reaction, before the reaction, nothing we know about what is happening during the reaction. So in situ advanced electrochemical techniques are coming up. There are very good technologies that they can make you understand like what exactly is happening. But so I guess next 10 years there will be very much improvement in these technologies, and then we can always reduce the losses and the cost of the materials. So more optimistic as of now.